myself Ankita, Faculty Department of IT, Akgec. So today I'm going to discuss local search algorithms and optimization problems. This is the third topic of Unit 2. Now, till now we have discussed about informed search techniques and uninformed search techniques. In both of these techniques, we were searching for the goal node and we were searching for the optimal path to the goal node. So we were exploring the search spaces systematically. Now this systematicity is achieved by keeping one or more paths in memory and by recording which alternatives have been explored at each point along the path. So when the goal is found, the path to that goal also constitute the solution to the problem. So we have till now discussed about the uninformed and informed search. In both of these search techniques, we were exploring the search space and we were trying to find out the best path to the node, and the path to that goal also constitute the solution to the problem. So however, there are some problems in which the path to the goal node is not relevant. We just need the goal node. We have to reach the goal node. For example, your 8 queen problem. Now in 8 queen problem, we have a board of 8 by 8 squares. We have 8 by 8 squares and we have to arrange the queens in that board in such a manner that no queens attack each other. So this is a problem 8 queen, and in such problems we don't require the steps how we are placing the queens one after the other, but what we require is that we reach a configuration on the board so that no queen is attacking each other. So in such cases, we don't require the uninformed or informed searches. We can do with your local search algorithms. So if the path of the goal does not matter, we might consider a different class of algorithm which is known as your local search algorithms. Now in local search algorithms, we search in a solution space where each node will be a solution. So in local search algorithm, what we do, we have many solutions in hand, and you can say each solution is a node, right? So that node will represent a solution, and that solution could be either a good solution or a bad solution. So our goal is to find out the best solution. So our task is to find a state which is optimal solution to a problem. So here we keep track of single current state or node. So we are only keeping track of the node. We are not concerned with the path we have chosen. We just only are considering the single current path. Second, we only move to the neighboring state. Therefore, we call it a local search algorithm because that we only move to the neighboring state. Third is the path followed by the search is not retained. Since we are not concerned with the path, we are only concerned with the goal. We don't save the path. Now, advantage is that they use very little memory. Of course, we are using little memory. Why? Because we are not saving the path. In your BFS algorithm, we were saving the entire frontier of nodes in your queue and stack, right? But here we don't need stack or queues. We just need store the current node. They often find reasonable solution in large or infinite state spaces for which systematic algorithms are unsuitable. Pure optimization problems, these are the local search algorithms. The problem that we solve through local search algorithms are pure optimization problem. Now, all state have an objective function. What does objective function means? The objective function means we tell us whether the solution or the node we have represents a good solution or a bad solution. So it tells about whether the solution or that is represented by a node is a good or bad. Our goal is to find a state with maximum or minimum objective problem value. So if it is a maximization problem where we need to maximize the objective function value, and if it is a minimization problem, we have to minimize the objective function value. So our goal node will be that node which have the maximum value of objective function in the case of maximization problem, and in case of minimization problem, our goal node will be that node which have minimum value of the objective function. Definition of local search algorithm, it is a very descriptive one. It says that it refers to a family of optimization algorithm that is used to find the best possible solution within a given search space. So we have a search space. In your informed and uninformed search techniques, we are searching in the partial solution space. Whereas in your local search algorithm, we are searching in the solution space and we are keen to find the best possible solution. So unlike the global search method that explored the entire solution space, local search algorithm focus on making the incremental changes to improve the current solution until they reach a local optimal or satisfactory solution. So it is making incremental changes to the solution so as to reach the goal solution. Now this approach is useful in situations where solution space is vast, making exhaustive search impractical. Now I will be explaining the the local search algorithm by n queens. Now this is your n queen problem. These are the queens that we have to arrange in the board in such a manner that no queens are attacking to each other. This is our goal node. So here we are trying to formulate an n queen problem as an optimization problem or a local search problem. Now here in local search, when we are defining a problem, we have to define what we call a state. Now a state in a local search is a solution. Okay. A state in a local search algorithm represent a solution. It can be a good solution or it can be a bad solution. So here we can decide at most one queen or in one column. So we have made an assumption that in one column we will be putting one queen, and all the configuration of the boards we are changing the position of queens and that each configuration will represent a node. Now, what is objective function? Objective function will be telling me whether my solution is a good or bad solution. Now, suppose this configuration of queens represent one node, and the objective function value of this will be the number of queens that are attacking each other. Suppose this is 1 attack, 2 attack, 3 attack. So here we can say what is the worst possible state? The worst possible state will be when every queen will be attacking each other. So we will be having 28 attacks, right? Now what will be the best possible state? When no queen will be attacking each other. So it will be 0. So the objective function here should minimize the attack until it becomes 0. So our task is to find out a configuration of the board where no queens is attacking each other. Now what is the successor function or neighborhood function? Now this function determines what next node will be. Now in local search algorithm we are only searching in the local space. Now when we are searching in the local space, we have to decide what is the next state that can be generated from this state, right? So here the intuition of neighborhood function is two states in the neighborhood are relatively similar solutions. So move single queen to another square in the same column. So we have assumed certain things. First, we are putting a queen in one column, one queen in one column. Second, we can find the neighboring state of this by moving a queen, only one queen. So if we are moving only one queen in the board, we can say we have reached the next neighboring state. Now what is hill climbing algorithm? Now hill climbing algorithms are the first set of algorithms that is used to solve the local search problems. Now it says that if I am at a node, I will be moving to my neighboring node only when if its objective function value is better than me. Then only I will move, otherwise I won't move. So this is the basic crux of your hill climbing algorithm. It says that I will continuously move in the direction of increasing elevation or value to find the peak of the mountain or best solution to the problem. It terminates when it reaches the peak value where no neighbor has a higher value. Understood? So suppose I am at a node, okay, and the objective function value of this node is suppose 10, right? Now I have to check whether I can, now suppose it is a maximization problems, and I have to consider those nodes that are near to me which have better value than mine, right? So suppose there are 3 nodes, and each of these objective function values are suppose 11, 9 and 7. Okay. So what hill climbing algorithm says that I will move to any of these neighboring nodes only when its objective function value is better than me. So I will move to 11. Why? Because its objective function value is better than mine. So I will move to 11. Now suppose the neighbors of 11, this node is 7 and 6 and 9. Now this 11, from if I am at 11th this node, I won't be able to move to any of these 3 nodes. Why? Though they are neighboring nodes, but the objective function values are not better than me. So well, I will assume that this is my solution. Okay. So that was your hill climbing algorithm. It says that it does not maintain a search tree because it is not concerned with the path. It is whichever node it is present at that moment, it will be storing only that node. So the structure of the current node need only the record the state and the value of the objective functions. Hill climbing is also known as greedy local search because and with no backtracking, because we cannot backtrack. If I have reached over here, I cannot backtrack to 10 to find out if there any better solution exists or not. So I will be only searching in my neighboring space, and if the nodes in my neighboring space have better value than me, then I will move to that node, otherwise I will stop. So hill climbing or algorithm often make rapid progress towards a solution because it usually quite easy to improve a bad state. So it quickly reaches to the solution if it is present, right? Now there are two variants of your hill climbing algorithm. One is your simple hill climbing and other one is your steepest hill climbing. So first we will discussing simple hill climbing. Now simple hill climbing just says that if suppose I am at a node and I have maybe 5 neighboring nodes. The first node that I find which is better than me, I will jump to that node. That is your simple hill climbing. It says that it only evaluates the neighbor node state at a time and select the first one which optimizes current set and it as a current state. So it only check its first successive state, and if it find better than current state, then move else be in the same state. So algorithm, I have a node 10, okay, and I have suppose 8, 9, 11 and 12. So suppose I have started searching from 9th. So I search 9th value, objective function value is less than me, I won't move. I will search 11. When I will search 11, so what I will do, its value is better than me, I will jump. I won't consider even 12. That is your simple hill climbing. Whereas in your steepest hill climbing, I will be checking all my neighboring nodes. Okay, so I will check 9. 9 is not better than me, I will reject. I will check 11. Okay, it is better than me. I can move there, but I won't move. I will check 12. It is better than 11. So I will jump to 12. So that is your steepest ascent hill climbing. It says that it examines all neighboring nodes of the current state and select the neighbor node which is closest to the goal state. The algorithm consumes more time. It searches for multiple neighbors. Obviously, it will give you the better solution than your simple hill climbing, but of course, it will take more time. Now, to represent a local search algorithm, we are depicting it in the form of a state space diagram. So what we are seeing now, first is your current state. Now, what do you mean by current state? Current state is at a point at which we have started our search process. We can start in any of these processes. So suppose that we have started from here. This is my current state. What is the global maximum? This is the best solution of that problem. So it is the best possible state of that state space landscape. It has the highest value of the objective function. It will be having the highest value of the objective function. So please mind it. This is your depiction of maximization problem. So in maximization problem, a solution will be maximum with objective function maximum will be represented by the global maximum. Next is a local maximum. A local maximum is a state which is better than its neighboring state. But there is also another state which is higher than it. Now this is your local maximum. Now this is better than its neighboring state, but it is not the best state. Flat local maximum, it is a flat space in the landscape where all neighbor states of the current states have the same value. So here we can say all of them have the same value. Now problem says, suppose we are at this position, right? Now my hill climbing algorithm say I will move to the next neighboring state only if it has better value than me. So now we cannot move there. So this is your flat local maximum or plateau. Shoulder say it's a plateau region which has an uphill edge like this. So there is some flat region and after that it's uphill. So a hill climbing algorithm always says that if I am over here, I will move only upwards. I won't move downwards. I will only move to those nodes which has better value than me. So that was your state space diagram. Now let's understand this problem by this problem. Okay. Now see, this is your 8 queen problem. Now our task is to achieve the global minimum, that with h is equal to 0. Now h is equal to 0 means no queens will be attacking each other. Now suppose we have started from this board configuration, and here my objective function value is 17. Now 17 means there are 17 queens that are attacking each other. You can say this is one pair of queen, 2, 3, 4, 5, 6, 7. Similarly, we can find 17 queens, right? We are attacking each other. So here our h is equal to 70. Now our goal is to minimize this, right? So what I will do, I will try to move some queens so that I can get lower value of heuristic. Suppose I have moved this queen because here it is minimum 12. So I am putting this queen over here. So my heuristic value will be 12. It is minimized. I have to move only one queen at a time. That is my condition because I am moving only in my local area. So with 5 steps, I can reach this board configuration where my heuristic value is 1. Understood? The movement of 5 queens. Which queens I have moved? I have moved this queen. I have moved this queen. Okay. And I have moved this queen. So likewise, I have moved 5 queens and I have reached over this whose heuristic value is 1. Now the problem arises that after this board configuration, I cannot move any of my queens so that my heuristic value get reduced in one step. So I cannot move any of these queens in such a manner that my heuristic value get reduced to 0. So this is your local minima. It says that my condition is that I have to move only one queen at a time, and I can move only one queen only when its heuristic value become less than this board configuration. But I cannot find any position of the queen that I can move so that my heuristic value goes to 0. So this is your local minima. So you can say 14% of time the hill climbing algorithm solve the problem, whereas 86% of time it gets stuck in the local minima. That's the problem of our hill climbing algorithm. It takes only 4 steps on average when it succeeds, whereas it takes 3 on average when it gets stuck. So main funda of local search algorithm is that it can give you results very quickly. It can either fail in that time or it can pass. So the main advantage of hill climbing algorithm is that it gives you solution very quickly. You can say it in 4 steps only it will succeed, and in 3 steps you will get to know that you are stuck and you have to restart. So how we can say that we will get stuck in the local maxima? It all depends on where we start. So if I have started over here, suppose if I started over here, if I started my movement over here, so I will definitely get stuck in my local maxima. But if I start over here, I will reach the global maxima somehow. So that is the, you can say that is the problem of your hill climbing algorithm. So we have to devise some methods so as to improve this. Now the problems are explained over here. First is your local maxima. Local maxima is this. A local maxima is a peak that is higher than each of its neighboring states but lower than the global maxima. Hill climbing algorithm that reaches the vicinity of local maximum will be drawn upwards over the peak but will then stuck with nowhere else to go. So if I start from here, I will definitely get stuck over the local maxima. Ridge result is a sequence of local maxima that is very difficult for greedy algorithm to navigate. Now suppose I am over here, so it will be difficult to move, right? So a plateau. Plateau is a flat. There are 2 types of plateau. First is your flat local maxima and another one is your shoulder. So a plateau is a flat area of state space landscape. It can be a flat local maxima from which no uphill moves are possible. So if I am over here, so there is no uphill move. All the values are same as mine. So I won't be able to jump to the next node. Now what is the solution for that? We can allow the sideways move. Suppose I am over here and I have allowed some sideways moves. So I can reach over here, right? When I am reaching over here, it's a possibility that I will reach the global maxima. So we can allow sideways moves in the hope that a plateau is really a shoulder. So if it is a real plateau, we won't be ever able to reach the global maxima. But if a plateau is a shoulder, we will be able to reach the global maxima. So we can limit the number of sideways moves right? We cannot, if suppose I am allowed sideways move at this point, so I will be indefinitely stuck in this loop, right? But I have fixed number of limits. If I put a limit of 100, okay, if I put a limit to 100, then we can say I can reach, if I am at this position, I can reach the global maxima. So for 8 queen move, if we allow the sideways move with a limit of 100, we can raise the percentages of solved problem from 14% to 94%. Earlier, my success rate was 14%. Now, my success rate is at 94%. It is a significant improvement. But you can also see that it takes 21 steps for successful solution and 64 to reach failure. Now, this is a disadvantage. So, if we are getting the solution, obviously, we are taking more time if we allow sideways moves. So, what are the variations of hill climbing to tackle its problem? The one is a taboo search and other is stochastic hill climbing variations. Now, taboo search says that I will be keeping the track of the nodes that I have already visited. Okay. So, to prevent the algorithm from getting stuck in the loop or revisiting state, a list of previously visited states can be maintained, which are then avoided in the future step. So, see, we can stuck in the infinite loop if we are keep repeating the nodes again and again. Okay. Suppose that I am at a node here and heuristic value is 10 and this is also 10, this is also 10. So if I'm allowing the sideways moves, now this is node A, this is node B and this is node C. I'm allowing the sideways moves. Okay. So if I'm allowing the sideways move, I'm at A, so I will allow, okay, my neighboring node is B, 10. I will reach there. My neighboring node is C, I will reach here, 10. But now, again, I will reach to A. Why? Because this A is also neighboring to C. So, what I am getting stuck in the infinite loop. Now, to prevent this, I will be keeping a taboo list. Taboo list is that I will be keeping the list of node that I have already visited. So, if I am at node A, I will put node A in the taboo list. And then I will move to node B, I will put node in the taboo list B. If I am at C, I will put the node in C. Now, at C, it might have another node with value 10. So, now C won't go back to A. It will move to 10 only. Why? Because A is already being visited. Also, we have to fix length. This is a list of fixed length queue called taboo list we have to keep. Now, as the size of taboo list grows, hill climbing will asymptotically become non-redundant. That was your taboo search. Second is your stochastic hill climb variations. So, when a state space landscape has local minima, any search that moves only in greedy direction cannot be complete. Now, what we are doing in your hill climbing, we are only moving to the better states. Now, if we are using that approach, it is very difficult that we get a complete solution. In such cases, we are using the hybrid approach. So, in stochastic hill climbing, we select one neighbor node at random and decide whether to choose it as a current state or examine the another state. So, we are choosing the node at the random. We are not choosing the node with the increasing elevation only. The selection probability can vary with the steepness of the uphill move. Now, to avoid getting stuck in local minima, we have three variations. One is random restart, random walk or hill climbing with both. Now, in hill climbing with random walk, we say with probability P, I will be moving to the neighborhood with the largest value, better value than me. And with probability 1 by P, I will move to a random neighbor. So, first, I am selecting my next node based on my objective function value. Though that node which has better value than me, I will move to that node. But in next way, I will just select a random node. So, by this way, with this called as hill climbing with random walk, I can avoid getting stuck to the local maxima. Now, in random restart, what we can do, whenever we get stuck at a local optima, randomly sample a value. Now, it says that in your random walk, I was just randomly, there was random, you can say interleaved actions where in first action, I was going to select the better node. In another action, I will be selecting a random node. But what does random restart says, whenever you get stuck in the loop, whenever you are not stuck in the local optima, then you can jump somewhere else with the any random node. So, this is called as random restart hill climbing algorithm, that whenever you get stuck in local maxima, just select another random node. So, this was your hill climbing with random restart. We can combine these two, that is random walk and random restart, and we'll get both. So, this was how we are tackling the various problem of your hill climbing algorithm. Thank you.